Hi all. I think last time we stopped at the overview, and I told about I'll be talking about assembly, and I have to introduce the prerequisites, which are assembly and make. See, this is the part which motivated me towards compiler and system software engineering. So this is like close to what I like what motivated me. So I would like to pass on that motivation to you, and hopefully you also get why I was motivated, and that would also motivate you people to be into system software engineering. So with that being said, so let's move it. Today I don't want to just show you just dry assembly, so that will bore you. That will not give you the essence. As in, I was motivated by assembly due to its capabilities. So that is what I want to pass on to you. Let me start by just telling how many of you know about this register. So there's this register keyword in C. So this register keyword is a request to the system to get hold of the register. So that say this A is equal to 5 is there, right? So if it's a 32-bit system, this 5 will be stored in a 32-bit register. So remember I told you this architecture, right? 32-bit x86. So this is the 32-bit register. So we have EAX register, which is a 32-bit, and we have that AX register. AX register, remember the AX register which I was talking about? That 8086, we had microprocessor microcontroller, right? Let me put image. So this AX, this also not that good. One second. I probably think this is good. No, that is also not. It's this good enough. So we had this AX register, right? Within AX, remember I told you in last lecture this AH and AL. So AH is 8 bits, and again AL is also 8 bits. So lower 8 bits is the AL, and AH is the higher 8 bits. So combinedly AHL is the AX register. So these are the four general purpose registers in which you use, and this AX is called accumulator. So today I'll not be going deep into all instructions, as in we have add, subtract, multiplication, division, all that I'm not going to. This will be a brief introduction because everything is not required for this compiler. I'll make a separate series for this assembly, and I also want to introduce you SIMD, AVX kind of subject, those type of topics. So there, those topics are related. I mean, there you have a requirement of multiplication and division. So I think I'll introduce it there because this is just compiler, right? So compiler, finally you are getting this code, right? As in a code of this way. where you are assigning into RDI and RX. So you don't have to even go through add instruction here. But still, I'll introduce you to add and also little about assembly and and not just the raw assembly like I told. This will be this will be combination of how you can call assembly functions from a C, and also there will be a uh, uh, little bit surprise for you, as in who is already this in itself. I might think most of you might be new to this, so this itself might be new to you people. I'll also show you another kind of thing that from assembly also you can call C, C functions. Okay, so I was talking about this register. So this register, using that register, we can get this register, EAX register. So this 32 bit. If it is 64 bit, it will be RAX, RBX. Yeah. If it is then, so if it is 64 bit, you will have RAX register, right? So this register is a request to your uh, system to get this register. So you might get or might not get. Okay. It's not 100% surety. And why do we use this register? We use this register so that this A equal to 5 is quickly available. Because in your CPU, register is the closest one, right? It is within the CPU. But your memory is a totally different area. It's not within the CPU, right? You have, of course, you have cache memory, which is within the CPU, your CPU chip. But this memory is totally out from CPU chip, right? So you have to connect through lines. So you'll have a delay there. So that's why you'll see that when you access your data through registers, it's more faster. And when you access data through your memory, it is much slower. Say it might take in say milliseconds. Um, and in your register it will take in sorry, not milliseconds, now you have microseconds. Okay, now it's in range of microseconds, so microseconds, and your registers would be in nanoseconds because it's within the CPU, right? So because of those delay lines from the CPU to your okay, let me just show you the CPU and so see, you have this CPU. CPU is an chip in itself, and your memory RAM is another chip. And in between, you have these lines. So these lines create a delay. Okay. So because of that delay, you cannot get your data quickly. And because there is another delay also, you have to go and tell this the data I want, this the location where I want to get. Okay. So there's a delay over there. But in registers, it's within this CPU. That's why it's very fast in terms of nanoseconds. And here it's in terms of microseconds, half microseconds. Fine. Okay, so back to where we were. So here it is request. Okay. Now what if we could really interact with the registers like the RX or BX registers? So that's what I'll be showing you today. So I've created these assembly uh, lines. Okay, assembly code. So So let's start with the two. See, as I told you, see, assembly is the code which targets your target machine. Okay. So based on your target machine, you have your assembly. So if it's 32-bit architecture, you have EBP, ESP, EAX, EBX, right? If it is 64-bit architecture, you have RAX, RDI, RSI. Okay, RAX, RDX, RCX, RDX. Fine. So now see, I'll show you like there are improvements from 32-bit to 64-bit. Okay. So starting with, let's start with a program file. Let's start with 32-bit and I'll show you what's the improvement in 64-bit architecture. Fine. So how do you access a function which is defined in some other file in C? You use the extern keyword, right? Extern, and then the return type and the function, right? This is how you use in C, right? Now, this sum 3 is defined in your assembly. Okay. In our case, this sum 3 is defined in our assembly. So what are the arguments here? We have firstly we have three arguments: long A, long B, long C. So A, B, C are the values we have. Three values we have. Okay. So there is something called the cdecl calling convention in 32-bit architecture. Okay. So I'll walk you through. So I'm showing you now how we can call assembly functions from C and how it is handled in assembly in 32-bit architecture. Okay. So, uh, so we use sum 3, right? External because it's defined not in this file, it is defined somewhere else. It can be a C file or an assembly file. Okay. So sum 3, remember this sum 3, and we have three parameters A, B, C. Okay. Now moving on to here. Now, sum 3 is going to be a label. Okay. Sum 3 is going to be a label. Now this sum 3 should be known outside to the world, like outside to the C program, as in this sum 3 is there. So that's why you have to define it as a global. Just like in your C program, you have global variables, right? Similarly, you have to define this as global so that it will be visible for your C function. Okay. So that this works. If you don't do this global, this entire sum won't be visible. Okay. So now this sum is going to be a function. That's why it's going to have a return. Just like how we have return over here, right? Return 0. It is int, so we return 0. So in assembly, your functions will always have a return, ret, right? This return. Okay. So now how we start with, we have stack kind of not stack kind of, it is stack. Okay. So what do you have here? Our parameters are this sum 3 long ABC, right? Before that, I need to clear here one more thing. See, it is section dot text. Okay, it is section dot text. So if you look at this, text is where you write your code. Okay. I need to show you this before that. For So executable and link format. Okay. So this is the format of your how executables should be in your x86 processor. Okay. So you will have these sections: text, read only data, RO data is read only data, dot data is your data. Okay. So text will be an executable. That section is where a code would be, and that section is you can execute it. Okay, it's an executable. But read only data, you can only read that value. You can't update that section's value. Okay. So these are sections of your entire program, and these sections has one-to-one mapping. Okay, to your separate segments. So let me show what I mean. Yes, this one. Uh, okay, this no, this is good. So if you look at this is also not good, right? Uh, hmm. So if you look at your text, which I shown here, right? This text, this text is going to map to your code segment. Okay, code segment. This is the part where you'll have your executable files, where your code, as in your entire this C assembly, everything, all these parts will be stored onto this location here. And your variables, right? These variables, these values, not these also will be stored in your data segment. Okay, this will be stored in your data segment, and this one, your extra segment is where you will have your heap. Okay, and this the stack segment. Remember, you might have come across this that when you call a function, it's calling a stack, right? You might have come across this, right? Like when you call a function, what you might be told about this, right? Like when you call a function, say if you have a main function, and within that main function, you have say some fu function, okay? And say this is line number, let's say this in memory 1000, this main, okay? And this is at line number 1000, 1001, okay? Hypothetically, hypothetically, is at 1001 location, okay? So your efficiency fund would have say return some 100, okay? And that value you are adding into your result. Okay, so RES result will have your 100. So whenever you are calling this function, and let's say this function is set, let's bring this below. Okay. Let's say this is set location 2000 in the memory as in your RAM, and this is say 2001. Okay. So as soon as when you call this function, you will jump to this location 2000. Then next you will go to 2001. And as soon as when you hit the return, you will return back to this 1001. And you see here it's a semicolon and followed by the next instruction. You say here it is something res plus equal to something say 100, and this at location say 1000, 1002. Okay, so then next followed by instructions get executed. So see, when you are going from 1001 to 2000, you are pushing this 1001 onto a location, a stack. Okay, 1001 is stored onto a stack, and when you are returning, this would be popped, and you are returning back to this line, and that's it. You are going then followed by you can go to your next lines. So that's why you have been told like whenever we are calling a function, we are invoking the stack. Why? Because we have your return address. This is your return address. Return address is where we have to return back after executing this function related definition. So in our case, it's this example, it's return 100. So after return 100, it has to return back to this 1001 address location. Okay. So okay, these topics I'll cover. Okay. I have to cover these as well. I had thought about so test section was done. Okay, and is done. I'll come to this topic will come. I just noted out, so that I don't forget about mentioning these points. So the extra segment is the runtime, the heap allocation. Stack is your stack. Yeah, here is where you use your ESP and EBP. Now it is the time to go about this stack segment. Okay, code segment is this entire portion will be stored on the code segment. So I told you right this entire portion, this text section entire will be stored on your code segment. Okay, and now coming back to our stack. So we have some long A, B, C, right? Okay. Now what we have is a base pointer, EBP, base pointer, ESP, stack pointer. So whenever you are calling a function, say you are calling sum3, okay, in that case, this return address, remember that I told you that 1001, it has to come back. So that line where we have to come back is what will be stored. So after sum3, what we have to do after sum 3? After sum 3, we have to go to this line, right? Line 18. So this value will be pushed onto your stack. How will be pushed? So your content of your stack will be return address. Okay. RET return address. Okay. Then followed by your parameters. A will be stored. Okay. Then next parameters B, then C. Okay. So this will be stored. So this ABC will be stored. And see, initially your stack ESP is a stack pointer. Okay. So initially it was at a level. Now when these values come up, it will increment. It will first return address will push, then these values will be pushed. No, sorry, first this C will be pushed. Okay. First C will be pushed, then B, then A, then finally the return address. So finally on top you'll have your return address. Okay. And the stack grows downwards. Okay, it's not the other way around. Downwards as in say you are at location 1004. Okay. Now when you push, say we are moving only one one byte. Okay. So say this 1004 is one byte. Next we are moving up. 1003 is next byte. Then we push again. Then it go to 1002. Okay. But in our case, it is 4 bytes, right? Why it is 4 bytes? It is 32-bit architecture. So in 32-bit, 4 into 8 is 32, right? So 8 bits is 1 byte. So 32-bit is 4 bytes. So at max, the data size, the smallest data size you will deal with in your 32-bit architecture is 4 bytes. So this A, B, C, even though it is long, you might have come across that long is 8 bytes, but this 8 bytes is dependent on your architecture. If it is 32-bit, you can have only your max of 4 bytes. Okay, you can access at a time 4 bytes. In 64 bytes at a time, max value of 8 bytes you can access. So that is where your long is 8 bytes. Okay. So now if I am at location 1004, if I push an element in 32-bit architecture, I'll move to 1000 location because stack count will grow downwards, right? So what I mean to say here is here we pushed now A, B, C return address is pushed. Finally, we are pushing automatically it will get pushed whenever we are calling this function because this function had ABC, right? So this will get pushed. The cdecl convention will handle that. It will automatically push those arguments, right? After that, we are pushing EBP. So on now on top we have EBP value. Okay. So we have to save the EBP value. The storing of that EBP value is really important because EBP and ESP are your stack related registers, right? So when you are coming out of this sum 3, so see sum 3 is in this line, right? This line. So when we are coming out of that sum 3, so what happens? We are coming back to this one, no? Coming back to this line. See line 15 we called sum 3, right? And after that function call is done, we have to move on to line 18, right? So when sum 3 is done, see when sum 3 is called, this function gets invoked. This function which is in our assembly gets invoked. So after this RET, it get back to our sum 3. Okay. It get back to this line and it moves to next printf, right? So for that, we have to maintain our EBP and ESP to our previous values because always stack registers are EBP and ESP. So that has to maintain our see when we are going back, we'll have main function, right? Main function is calling this function, right? So main function will have EBP and ESP value associated with it. So that we have to preserve. That's why we have to keep back that. That's why we push that EBP value and pop it back. Okay. So now see now EBP is at top of the stack, and this is exactly where our ESP is. Okay. And right now, at this point, EBP and ESP are pointing at this same location, right? Because we did move into EBP, ESP. So move into EBP, the value whatever is in at ESP. So that pointer is moved into EBP. Okay. So move is like this. Move. So semicolon in assembly is comments. Okay. Semicolon in assembly is comments, just like in C we have this double slash, right? So semicolon in assembly is comments. So move this one. destination and source. Yes, SRC. So what happens here is DST equal to SRC. This is what happens. Okay, so that's what happens. So in EBP we'll get that pointer. So now if we do plus, see this is 32 bit, right? 32 bit. 32 bit is 4 bytes. How? 32 equal to 4 into 8, right? 8 bits is 1 byte. So 4 bytes, right? So each address associated with 32 bit is 4 bytes long, right? So if you do plus 4, you'll reach this address, which is containing return address. If you do plus 4 again, which is plus 8, you'll reach this A. So by doing EBP plus 8, EBP and ESP are pointing to the same location, right? So even if I do ESP, it's the same thing. Okay, ESP. So let this be ESP, just to show you, or let it be ESP for now. So ESP or EBP plus 8, you will reach A. Now again plus 4. Plus 4 is how much? 12. So plus 12 will be your B. Again plus 4 is 16, you will reach C. Yeah, now why it is ESP plus 8 and not minus 8? So as I told, this stack is growing downwards. Okay. So whenever you push a value, so from 1004 I told, right, goes to 1000. Okay. Now again if you push a value, so it will go to minus 4, which is 0, 9 and 6. Again if you push minus 4. So 0, 9 and 2. So this is for your 32 bit. So which is 4 bytes. Similarly, if it is your 64 bit, it is 8 bytes, right? 8 eights are 64, so 8 bytes. So it'll move down by 8 bytes. Okay. So that's why, so right now, let's say we started at 1004 location. Okay. Let's map this with this example. Let's think that RSP initially nothing is there. Before call of this function, RSP is at 1004. Okay. Now when this is called, all these values will be pushed, right? Three values and plus this return address. This is what your cdecl convention will take care of. So automatically all these parameters, as in your C will be pushed first. This parameter will be pushed first. So automatically minus 4. Okay. Again it will be pushed. So minus 4 is 0, 0, 0, 9, 6. Okay. Then this is what? This was your initial RSP. Okay. This will make it separate. Then when you called some, what was the name? Sum three. When sum three function is called, sum three function is called, this is the location where your C is. Then this is your location where your B is. And then this is your location where your A's. Okay, so A, B, C are done. And finally, we have to have that return address. Return address of what? That we have to finally return back to our this 18, line 18, because this is where our function is being called, and that see function is being called from this line, right? This function sum 3. After that, we have to return to this 18th line, right? These are comments, so comments doesn't execute, right? Comments don't have an associated assembly with it, only printf. So it has to return back to this 18, line 18. So that return address will be the address in memory associated with your this line 18 in main C. Okay, that printf line. So that return address 0 minus 4 is how much? 988, right? That is your return area. With this line 18 printf. Okay. Okay. 918 9.cp 918. This is printf. Yeah. Then this is your return address. Again, we have pushed what have we pushed EVP. So minus 4 again. 4 bytes, right? That 2 bit have we reached. So 9, 8, 4. This is finally your EVP value. Okay. Now see, EVP and ESP are at the same location. Double equal ESP. Why? Because of this instruction. Move EVP comma ESP. Okay. So if we do EVP plus 8 or ESP plus 8, what will happen? Plus 8 will reach here A. So we reached here. So EAX will have the value A now. Okay. Same. Here move EVP comma ESP, whatever value the pointer will be given. So here in that pointer, see when square bracket is done, right? It is the value at that location. Okay, the pointer. Oh, we are dereferencing the pointer. So value at that location will be passed on to EX. So value at that location is so here we are giving the address. Okay, this is the address of A, B, C. Okay, the value at the location. So here it was 1, right? So that 1 will be passed into EX. Then that A value will be added with this next one B, which is 2. Okay, so 1 plus 2, 3 is done in this step. In next step, 3, 1 plus 2 is done, right? So 3. So 3 plus this 3, which is 6. So 6 will be stored in EAX. Now that EAX, this AX register is accumulated. Okay, it's accumulated. So often when you return back from the function, EAX is the register, the value whichever is contained in EAX that will be passed as your return value. So when we are returning here, that EAX value will be given on to your result. So that 6 was stored in RAX, right? Sorry, it was 32 bit now. So 32 bit your EAX register. So that 6 value was in EAX register. So EAX register's value 6 will be stored back to here result. Okay. So finally result will have the value of EAX which is 6. And finally it will be stored. It will be printed out. So let's go through this. So commands for this for 30-bit architecture. So if I run this, okay, it was 32. See, it is 32-bit architecture, right? So I have to inform the assembler that my target machine is 32-bit. So ELF 32. That's how I tell my assembler that you need to generate a 32-bit machine code. Okay. See, the compiler was it has to it will convert high level language to your assembly code. Now assembly will convert your assembly code to your target machine code. Okay. So target machine code could be 32-bit or 64-bit or any other. It could be a RISC kind of processor or a CISC kind of processor. There we have different methods. So right now, this will create an object file called add.o. Okay. It is not an executable file. It's a machine code which is not executable. It's just a pure machine code. You can't, it's not executable. And now we have to link this to our main C. Okay. We have to link this to our main C file. So for that, we have to tell GCC also that we need a 32-bit executable, and we have to link main C and add dot home. Why we have to link? Because here that sum three is there, right? Is sum three is been defined earlier, right? Here sum three is been defined earlier. So we have to link this so that it gets to know, okay, this sum 3 is being defined in this add 32.asm. Okay. So that object file which is containing add 32.asm is add.asm. Okay. Now finally running my program, add program, this is my final binary for an add 36. Okay. So if I change this value, say 30, okay, should give 33. And this time I don't have to redo this one because the object file I didn't change, right? And the assembly I haven't changed. What I have changed? Only this main.c. If I run this, because I only changed my C program file, right? If I run this again and this, I get 33. Okay. So now I have three arguments here, right? Instead of three, let's say I add 1, 2, 3, 4. Yeah. Now in that case, firstly here I have to change long t. Okay. And here I have to change this. Which is add dot lesson. The add dot lesson is 64-bit. Okay. This is our 32-bit architecture. Okay. So if I come back to here, what did we have? We had sum 3, right? So let me change it to sum 4. And our function is, let it be sum 3. And it has long d. Okay. So this time instead of ABC, I will have d as well. So it is 32 bit, right? So 4 bytes have to add 4 bytes as in 32 bit. So 20. So EAX will have the return value, which is the sum of all this. So basically, it is going to be 4 into 5 divided by 2, which is 10. Okay. So if I'm running this now, NASM I have changed, right? So after run this, GCC, and then finally this, so 10. Okay. So this is how it will work. So now, see here we are dealing with stack. So stack you have to push the value, then you have to read the value. So pushing itself is a time consuming process, right, onto stack. So now you will see an improvement in our 64-bit architecture. So in our 62-bit architecture, if you look at, let me count this out, I have now some 8. Okay. And next one is, so I have 8 targets. This is the okay. So I have the 8 target. Okay. Mm, okay. So now here in 64-bit, you'll see that for 6 parameters, 6 arguments, we directly have registers RDI, RSI, RDX, RCX, R8, R9. Okay. See, in 64-bit architecture, you have more registers than a 32-bit architecture. So it is utilizing those architectures, that registers. So that architecture is being used here. It is being utilized here directly up to 6 arguments. We can fetch it directly from our registers. From there on, we have to use our stack because beyond 6, we don't have registers. From seventh argument we are using our ASP. So there in our 32-bit we had cdecl convention, right? Here it is System V AMD64 calling convention. So this is the calling convention in 64-bit. Okay. So if we run this now, uh, firstly we need to have NASM. Yeah, NASM is right now 64. And it's not 64, it's add dot ASM 64-bit. Then we have GCC, and GCC we have to okay, now's the time I have to introduce this concept introduce you to this concept as in what is uh, PIE, positional independent executable, and positional independent code. Okay, so positional independent executable and positional independent code. So positional independent executable is what? Executable is your binary, right? So it is the one which see this add program is there, right? This add program is my binary, so that is my executable. Okay. And independent code is what? Independent code is just my raw machine code. So it's not an executable. So like this add dot o, okay, that's my machine code, but it's not executable. But in order to be positional independent executable, our code should be positional independent. Firstly, only it can be positional independent executable. So why is this important? So there is this concept called ASLR. Think I have opened it from there. Yeah, this one. Huh. So, um, so here you can see these are the see this a timeline. Okay. Firstly, my library code heap and program code is in this sections of my memory, my RAM. Okay. Next time when I run it, my program code shifted up and library code shifted down. Next time when I'm running it, running the same executable, library code shifted up, program code shifted a bit more. Okay, so what can you see here? The your code is not at a fixed physical address. It is being shifted up and down. It's randomly shifted. So why is this useful? This very useful as in, see now if it was at a particular fixed location, now it would be a predictable, right? It's very predictable. So an attacker can say if it's say your library code and all this stuff is loaded at location 1000. Okay, so it's very predictable, right? If it's a fixed value and there only your entire code is loading, your attacker could load in to that location 1000 and they could attack, right? They could introduce malware over there. So that introduces it's a predictive situation, right? So now when you have randomization, now it's difficult for the hacker to get into the system and inject in code. So this brings in the randomization and brings in more security into your operating system. So now it is not just compiler design, it is also operating system. Okay, you need to know your operating system stuff also. So I have also written here, see, we have real mode and protected mode. So protected mode in real mode. Our 8086 used to work in real mode. Okay, ancestor of our present in laptops, x86 laptops. So 32-bit and 64-bit. It used to be in real mode. So what is real mode? So in real mode, you see you have this concept called first physical address. It is the address of our memory directly direct our RAM addresses. It is dealing directly with our RAM addresses. So here it is introducing predictability as I told, right? So it's a security issue. So attacker could say the same 1000 location your code is loaded. So attacker could easily say easily predict location 1000 your code is been loaded. So they could inject in that location a malware. Okay, so it is working with direct physical addresses, right? So from there we move to protected mode. Okay, in protected mode we have this concept called virtual address. So what is virtual address? Firstly, say our physical address is from 1000 to say this is a hypothetical situation where our location is from 1000 to 9999. Yeah. These are real locations in our RAM. Okay. Now let's say we want to map a location 100. Okay. Now this 100 will be assigned to your code. Okay. But this 100 is not a real address. This is your virtual address. So virtual address will be mapped to your say 2000 and say we could also map 10,000 or a lakh. Okay. To say 5,000. So now this is providing another layer of abstraction. Now the attacker will not know this 100 is actual 100 in our RAM. Okay. They would feel like that 100 is a actual address in RAM, but it is not the case. So this 100 and this one, this mapping of this 100 to 2000, all this stuff is done by OS developers. So this mapping is done by OS developers. Right? So here, this positional independent code, again, it's giving another layer of security to our code, right? So that's what it is doing. And here, I had to put this no positional independent code flag because, I'm manually setting up all these, right? See, I'm manually setting up RAX, RDI, and all this. If I'm not doing this, just running the C program without calling the assembly, the GCC would do this stuff, right? Internally. Okay. So, but here I have to do this, I'm doing this manually, so this would create an issue because this is not an independent code as like this text section will not treat it as an independent executable. So I had to introduce this flag. So now if I run this and now if I run add program, okay. So answer is 36. So is it 36? Let's look. So it's 8. So n into n plus 1 divided by 2, which is 8 into 9 divided by 2, which is 4 into 9, 36. Yes, it is 22. So let's say we add 4. So 1 into 8, 8 is 12. So we should get 40, right? So let's see. So here we just have to do the GCC part because NASM part we didn't do any change, assembly no change. So we run this as 40. So done. So now what did we see? We saw 64-bit and 32-bit architecture. Uh, we are calling the assembly functions in our C program, right? Now, what if I told you, like in our beginning, what I told, like, what if we could call C related functions from assembly? Wouldn't that be awesome? So that's exactly what we are going to see right now. So we'll start with 64-bit itself. So this is sound 2, okay? Sound 2. So let me comment. Now before commenting, let me just tell you, let me just say long I am doing, okay? And let this be here, and let this be mine. Okay. So, um, so plus 8 is 24. So now this is the ninth argument, right? Ninth argument. So ninth argument is 24 plus 24. Why? Because plus 8. Because see in 64 bit architecture, this is our RSP. See, stack moves always downwards, right? So minus 8, it goes this way, then minus 8. So 0, 9, 9, 2. So this is the way. So if this is the last value, here our RSP file will point to. Okay. So that way, why is it plus 24? Right? Because this RSP plus 8 will give me this value, plus 8 will give me this value. So RSP plus this 16 plus 8 is 24. So I'm at ninth argument here. Okay. So now if I run this, it should give me 9 into n plus 1 step, right? Which is 45. 9 into 5, right? 45. So this time I have updated my assembly. So I've done this and also this. And then finally this 45 is minus 5. So you get it right. So if I have one more parameter, I have to add here plus 8 once more. So RSP plus instead of 24 plus 8 is 32. It will be the next one. Okay. So this done. Now I was talking about. this one. What if we could call, say, scanf is defined in studio.h, right? std.io.h. So what if scanf I call in, if I called in my assembly related function? Wouldn't that be awesome? So that's what we are going to look at right now. So we have some, and we look at this one. So see, and see, these six parameters like to right? These six arguments, RDI, RSI, RDX. So this you can see it being reused again. Okay, while interview. So firstly, it should be extra. Just like our C program, we had to do this extern sum 2, right? Because sum 2 is defined in our assembly. Same way, exact same thing. Scanf is defined in our stdio.h. And where is it? It's in a different file, right? It's not in this file. So we have to define here extend scanf, right? So that is done. And now see, in scanf we have this format specifier followed by this memory location as in A and B. So sum 2 is like A plus B. So it will return the value A plus B, right? So this RDI, same thing, exact same thing, RDI and RSM. So RDI I'll push in my format specifier, then my variable A. Okay. So RDI will have this format specifier. So format specifier is this one. Now there is this db. db is bytes. Okay. Now let me introduce you to this. So db. Yeah. So db is byte. Okay. dd is double word. Word is dw also. Yeah. Okay. dw. dw. dw is word. So word is 16-bit. Double word is 32-bit. DQ, quad word, is 64 bits. Okay. So all of this we have in assembly. But here we'll use DB. Why? Because see, this input format is going to be a pointer. So you can think of it as a pointer, and see, this pointer will go up to n. See, when should we in printf or printf, up to when we have to go? We have to go until, see, that string, until when we have to go, until we get a null character, right? So that null character is appended in assembly like this. We'll put a comma and after that it's null, 0. So percentage LT, this is our input format. That's our pointer. That pointer is put into this RDI. Then next is our A. Okay, that A will come from our RSI. See, this LEA is load effective address. So we are loading the effective address of this input format. Okay, so basically we are loading in this format, this input format wherever it is in our memory. Okay. See, this is section dot data. I have to clear this also once. That we had gone through this one, right? Is it? This one. So this part is loaded in our data segment. Okay. So this loaded onto our data segment. This stored in data segment. So load effective address of this input format. So REL will see relative to this instruction where is our input format. So from here it is at this location, right? And it is at data segment. So that effective location will be stored into RDI. So RDI will have the pointer to our format specifier. Okay. So here we are having our register, but in cdecl, this AMD64 polynomial version, right? There we won't have our RDI. There we'll have our push. Yeah, here I have commented out. So where was it? Push. Okay, we'll use push. Fine. So and RSI is our RSP. And one more thing here. One more very important thing here. See, I need to give space for this A and B, right? These are variables. So I'm giving it space in our stack. Okay. So say our RSP is right now at 1008. Now 1008 minus 8 because it is 8 bytes, 64-bit architecture. Okay. This I'll give for one of the variable. Next variable, I'll give it again minus 8. So 0, 9, 2. Okay. Say this I'm giving for A. And this my updated RSP. And this is my P. Okay. So this should have been 16, right? Should have been 16 because 8 plus 8, 8 for A, another 8 for B. Should have been 16. And see that RSP value uh, I have to not manipulate my RSP because RSP and RBP will be used by my main function as well, right? So that's why I have to finally subtracting I have to add back 16 as well. See, this will not work. Why it will not work? I'll tell you the reason, but let just show you. Just I'll run this, and define the reference to something. Okay, function main undefined reference to something. Okay, let's see. Is it defined as global? It's not defined as global, so it's not visible to Wi-Fi. So global will make it visible. So if I run, no, I have to run the NASM again. So because I made this change, so NASM and this. Then if I run or add program, I'll get a segmentation file. So why is it happening? Why it is happening? Because in AMD64 calling convention, when we have a call, right, this call, it should make sure that it is 16 bytes aligned. So when I do this 16 and when I do this call, okay, here it is 64 bit. So it is 8 bytes. So 16 plus, so it is 16 plus 8, which is 24. This 24 is not 16 byte aligned. Okay, it's not 16 byte aligned. So if you do 24 modulus of 16, it is 8. So modulus operator is the remainder operator, right? So you get 8, right? So that's not what we want. So what we want is, so we have to make it 16 byte aligned. So what we'll do is add another 8 bits. So it'll become 24. Now when this call will happen, we'll put in again 8, which is 32, and 32 modulus of 16. So remainder will be 0, right? So that's why I have to add it with this 24. And finally here also I have to add back the 24. Okay. Now if I run this back, okay, yes, I have to run this and this. Now it runs. So now see now this scanf is there, right? Again, one more scanf I have. Why I have done RSP plus 8? Because my RSP is here. So if I do plus 8, I'll reach over here. So for B, okay, for B. So again, I'll reuse this format specifier. I could reuse the same format specifier, right? So I'm reusing it. And Now if I enter 12, 13, I should get 25, right? 13 plus 12, 25, is that 25? So like that. Now if I want to add a third value, okay? So this the third, so plus 8, okay? Because I'll go again back by 0, 9, 8, 4, right? 8, 4, okay? This is my A right now. This is my RSP. This is my B. This is my C. Okay. So here it is not RSP plus 8. This one, sorry. It will be plus 8. So 16. Yeah. So now it is add B. We have to also add C. Okay. Now I have to update this C and input C. Okay. So now I am doing, before it was A plus B. Now I'm doing A plus B plus C. Okay. So my finally my RAX will have A plus B plus C. Okay. And as I told, accumulator the AX, EAX, RAX will have the return value, right? So that will be assigned to our result. Okay. So plus 8, which is 16. Fine. Now, do you think this will run? Do you think this will run? This will run. Why? Because already it is aligned. 24 is aligned. 24 plus 8, which is 32, is aligned. And also this 24 is 8 threes are 24, right? So we have space for this A, B, and C, right? So three variables we have provided the space as well. So this should work perfectly. It should work. So if I run NASM, then GCC, then I program. So now if I do 12, 5 and 7. So this is 24. Okay. Now again if I run 12, 6 and 7. So this is 6 plus 7 is 13, 25. Okay. So it works perfectly fine. So now if I add one more, third scanf, right? If I add one more, fourth scanf. So plus 8, right? Plus 8 is how much? 24, right? Plus again I added, right? So 0, 9, 8, no, 7, 6, right? Plus 8 half. So now this is my A, RSP, and this is my B, this is my C, this is my D. So now if I add plus 24, I'll reach over here, right? 1000. And that is exactly where my D is. Okay. So if I do this D and this is D and what else? And here also I have to change. This was move, right? So move I'm loading into RAX A and B, then C, now is D. Okay. Here move I was moving into RAX, the value. See the bracket is dereferencing it. So dereferencing the address of A, you'll get the value at that address. So that value is stored into RAX and that value is added with our B, then C, and now D, which is 24. Right. So now do you think this will work? Firstly, it will not work because we have only allocated space for three values. So 8, 4 are 32. How do you think it will work? We have allocated, right? It will not work. Why? Same reason. That 16 byte align. So if I do now add and give a segmentation for it. So this 32 plus 8 is 40. 40 more or less See 40 modulus 16. Okay, is what plus 8, right? Plus 32 plus 8. Now, if I add 8 to this 48 modulus 16 is what? 48 modulus 16 is 0. Okay, so now if you look at it is 16 byte line, right? So that's why, see, we had this segmentation part. Now, if we remove this and make it 40, and this 40 we have to add it earlier back, okay, so that we reach back to our final RSP so that our main function will not have any issue. So, uh, 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 40. Now, when this being called, it will become 48 and it is 16 byte in it. So now if we run this, now four values have printed in, say 12, uh, 13, 25, and 25. So it is basically 25 keys, 75, okay, 75. So this is how it will work. So isn't that amazing? We learned, see, first what did we see? We are calling assembly related functions from C. Now we are calling assembly related functions from C and also C related function from assembly. So isn't that amazing? Like, see, this word like excited me in this field. Okay, so I hope I could, bring in that excitement to you guys also. So, so okay, this is 64 bit. Okay, 64 bit we could easily use this REL. Okay, but in our 32 bit we can't use this. We have to come up with a different approach, as in, like, Indian word we use, right? Jugaad we have to do here. So the jugaad here is okay. It's the same sum two. Same sum two is what? Initially, just like our 64 bit, we'll start with a plus b. Okay. See, the jugaad is like we don't have REL, right? So we can't reach till this point. Firstly, we need to have this. Okay, just like that. In 64-bit, we had this exact same thing, and also we need to have external, and this sum two should be visible to RC, and scanf is external dependent. So that's counted out. Okay. Now, so we are calling this function. See, call will call a function. Just like here also we did call, right? We did call to scan. See here we did call to scan. So this will call our C related scanf function. So same way here we are calling. Okay, we are calling this function. But now see, this is a label in assembly. Label doesn't have label is not an instruction, so it won't be executed. So see this line 7, line 37, line 35, all these will be executed. Line 38 won't be executed. Line 39 will be executed. So now when we are calling a function, it will have a return address, right? So the return address is the next address, next point what we'll execute. So if we ignore this 38 line, okay, the next one to be executed is 39 line, right? Because as I told, label is not been executed. So the CPU will not execute this instruction. This is not an instruction first. Firstly, it's not an instruction. This is an instruction. This is an instruction. This is an instruction. Okay. So next, this line 39 would be our return address. So I told, right, like whenever we do a call, we'll have return address, right? See, we had this stack, right? Return address and then these parameters, right? So same way, this return address will have this line 39, and this line 39 is what will be pushed onto the stack. Okay, and that line 39 we are popping out. So basically this ESI will have this address, this 39 line address. So now using this ESI we can go back to this. Okay, so that's why I have written here this will be the current address. So this ESI will have the current address. Why? Because after call this is the instruction, right? And this is the instruction that is being executed on the CPU right now. CPU is executing this instruction, and it is having and it is this ESI will have, see, return address will be at the top, right? So that address is stored into this ESI. So that's why the current instruction will be stored into ESI, because we are copying that value into ESI. Okay. So again here, as I told, we'll be using there in 64-bit we had RDI and RSI, right? Registers. So here we don't have registers. Here we have stack. In cdecl convention it is stack. In AMD64 calling convention, up to six your arguments you have registers. After that only you go for stack, right? So here same thing, exact same thing. We have to go from ESI plus input format. So we'll reach this place. But see, we have these, right? These are like offsets. These are coming in between this input format. So we need to clear off this offset. So that's why minus get EIP. So that offset is being removed. And then we'll get this percentage LD, this address we get. Okay. So that is stored into EDI. Okay. And this LEA, as I told, load effective address, right? Again, now here we have the format specifier percentage LD. Now next is our this one. We have to store this A, right? We have to store this A. So how are we doing it? See, what are the contents of our stack now? The contents are, firstly, we had this return address we had. Then what did we do? No, before that, we had push EBP. Okay, push EBP. Mm, So we'll start at this sum 2. When we are at sum 2, so at sum 2, we'll have this return address. So return address of what? Return address of this line 20. Yeah, because after sum 2, we don't have anything to execute here. We'll go here. So main C 20th line. Main dot C 20th line. Okay. This was our, what was this? This is our RSP. Sorry, this 32-bit, right? So ESP. Okay. Then, then, then what? Then we are moving EV into EVP ESP. Okay. So EVP double equal ESP. Okay. Then what are we doing? Then we did subtract 8. Why 8? Because we need to allocate A and B, right? A and B. So A will take up 4 bytes, B will take another 4 bytes. So 4 plus 4, 8. Okay. So right now ESP is over here. So we have B here and say A is here. And our ESP are here. So ESP now moved and EBP remained over here itself. Okay. So ESP moved and this one here. Okay. Then we are doing this call. Okay. Then we are doing this call. And this call is what? This call will have our add 32 sums. Which line? This line will have 39. Because that's the next instruction will be executed. Okay. Line 39. Okay. Now, so ESP is pointing right now over here, not here. ESP is right now over here. Stack pointer is right now here. Our EBP is still at this line. Okay. So then we are popping that value into ESL. So this is gone. Okay. So now ESP is pointing back to our ESL. And this why did we do? Because this REL will not work, right? That's why we had to do this jugaad. Okay. So this jugaad we had to do here to get that REL kind of functionality here. So then this is our stack content right now. A, B, return this, right? Then we are pushing into that EAX. Okay. So what is EAX? What is EAX? EAX is our address, our A value is being pushed, right? So EAX is having the address of, so ampersand of address, right? Because see this load effective address, right? LEA, load effective address. So it is having address of A, and EDI again, that is also load effective address. So address of this percentage T, that is also pushed. Okay. Because in scanf we need two inputs, right? Remember here. Scanf we need two inputs, this format specifier and this address, right? So this format specifier here in 32-bit we don't have registers, right? We have this stack, so we have to push these values into stack. So first is this format specifier, right? So that's why it has to be at the top. It has to be at the top because at stack the topmost elements gets popped, right? So first is this one we have to take, then followed by see in scanf this how we have, right? First we have to get this one, then next is our location. So similarly here also first we had RDI where we are picking up our format specifier, then followed by our location in this ampersand. Yeah. So same thing, exact same thing. So our stack will have the topmost element, right? So we get to access this format specifier, then followed by our address ampersand A. Okay. So this is what we have. Okay. So let's start assigning addresses so that we don't lose track. First, let this be say 1008. Okay, and let this one be minus. No. Okay, so this is 32-bit architecture, right? So 1004. Then this is 1000. And this is minus 4 is 0996. Minus 4 is 0998. 0998. Okay. So EBP. is at 1008, right? EBP minus 4. EBP is pointed to this location. EBP minus 4 is 1004. So this will point to our B. Okay. So this will have, so okay, in my case, I have reversed this. This is A, this is B. Okay. So this ampersand A is, this will store 1004. Okay. 1004. Okay. So minus 4. So EBP is 1008 minus 4 is 1004. Okay. So that's why the this is here EBP minus 4, right? See, EBP minus 4 is this location, right? So this 1004 should be loaded, right? That is why I have loaded this load effective address of this A into our EX register. So VP minus 4 will have our A register's address. Okay. So that's how we pushed this 1004 and this first stage LDR format specifier. And then we call, and then we have add ESP8. Okay. So why is this? Why do you think why we are adding add ESP8? So we did push EAX and EDR, right? So exactly. So here push EAX is 4 bytes and this also 4 bytes. Why 32-bit architecture, right? So instead of pop, which will consume time, so instead just to add ESP so that you will come down. Okay. See, we are clearing out this part. We are bringing down CESP until this line, before this line. Okay, till here, ESP was over here. Okay, ESP was here. After this, when we do add ESP8, okay, see, when we call the scan up, there also ESP and EBP will be manipulated. But see, uh, when we do add 8, okay, plus 8 is how much? 998 plus 8 is how much? We reach B, right? Why are we doing this? Because again we have to push. See, now for B we'll do ampersand of B, right? So for that we remove this part, okay? And we'll do this. Fine. So instead of doing pop, see pop we have to do pop EAX then pop EDI, right? See, topmost is right now EDI, right? So pop, we could have also done like pop EDI and pop the value. No, whatever is in EDI, pop it back to EDI and pop. And now after this topmost is EX, right? So pop EX. See, when we do push this one, yeah, when we do this, yeah. So first one EAX is pushed. EAX is pushed. Then on top of this, we are pushing EDI. So EDI is at the top, right? So we could do this also. This also works. So let this stay. But this time consuming. You could just add 8, okay, and your ESP will point down because it's just a one step. Okay, we are just coming out. You might think like we could have cleaned up those space, right? That region, but it doesn't make a change. You are bringing down your ESP, right? So ESP is what matters. So ESP is the accessibility range. So that's why in C and C++ you get your garbage value, right? So these garbage values are coming from these. Yeah. So these are the optimizations that we'll do in our assembly. Okay. So this will also work, clearly it'll work. So now again. Now EBP minus 8. Okay, EBP minus 8. So if we do minus 4 will reach here, minus 8 will reach here. So that's what it's been done here. So address of B and EDI, push into EDI. Okay. Uh, Also load this, right? Huh. Uh, okay. Huh, this will work because we had loaded the F device, right? And we are pushing it back. No, we are popping it back into EDI. So, uh, okay, that is fine. Or we could just do EX for, to double confirm that we are not messing up this EDI. Because EDI contains this format specifier, right? So we should not mess that up. So pop EX, and finally we are uh, again rewriting into EX. This works. Okay. Now finally we are adding EVP minus 4. EVP minus 4. Okay. Uh, so scanf we called, right? From scanf we are getting back our values, and those values will be written into this location and this location. So EVP minus 4. So move into EX EVP minus 4. So EVP minus 4 is our A, EVP minus 8 is our B. Okay. So add into that. So finally, and we'll get into EX, the accumulator will have our addition result. So finally, when we do this result, we'll get that result. Okay. That EX value will be copied into a result. Okay. So let's run this code, right? Uh, so this was had 32 had 32 20s, and it was Jay-Z. Okay. Uh, okay, there's one issue here. See, this worked for me when I put this flag. No, it worked. I don't know by fluke, but if anybody in the comments can tell me like what's the reason this worked, it would be great. Okay, I would appreciate that. So then finally, if I run this, so now I have to uh, same thing 12, 13, so 25. See, it looks so 12 and 7, so 19. Yes, it looks okay. So now similarly, if we want to expand this for 3, okay, for 3, same thing, scanf, okay. Uh, Here we had two variables. If we have A, B, C, right? 4 threes are 12. Okay. Now EBP minus 4, EBP minus 8, EBP minus 12. Uh, huh, huh. Okay. And so you've seen this, right? This works the same way. Just that here you are wasting it. So to in order to optimize it, you can use add ESP, comma. Okay, it works. Right? It works. I'll run this code and show you. Okay, and here it is. P minus 12, and finally over here, have to do EVP minus 12. Okay. So now if I do NASM is changed, right? and this one, and if I run this, right, um, 5 and 7, 24. See, so this is optimization. See, popping you have to pop one by one, right? So that's time taking. Here, one instruction is covering that entire thing. And also your bytes is reduced, right? See, before I had to write pop. See, before what I did. See, this will take up extra bytes, right? See, all of this will take extra bytes. So I reduced it to just one instruction. So my number of bytes for this particular code is also reduced. So say you are working on an edge device, embedded system, where memory is very important situation. So your lines of code is important. So if your lines of code are lesser, that bytes will get reduced. So you have to think about that also. Okay. When you're writing the code, you have to think about how, especially in embedded kind of situation, you have to think about how I can reduce my number of lines of code. Okay. So that it can fit into my limited RAM. Because in edge devices, you won't have like 32 uh, GB or 64 GB of RAM. You'll be limited by 4 GB, 2 GB RAM, right? So that lines of code plays crucial here. So similarly, if I have four, 4 into 4, right? 4 bytes, right? 4 bytes is 32-bit, 4 into 4 variables I need. So instead of this 12, I'll have here 16. 4 4 is 16. And here one more I have to do EBP minus 16 and EBP minus, uh, and here also I have to add EAX, EBP minus 16. So you get the flow, right? So Hariba is like excited now. Like, see, you see the combination, right? This is how your program will be on your OS, and uh, uh, and this part of this position independent, executable position independent coding. These you might have seen it in, like, theoretical view. See, you are seeing this in a practical view, right now, right? So isn't this exciting? So, and also I told you about that real mode and version, that protected mode, right? So these are layers of security that came over time. So even this position independent, executable position independent code, these are all, again, another layer of security. So see, this operating system, compiler design, computer architecture, these are like, brothers or sisters. They are totally related. Like, they're totally correlated. Okay. So if you are looking into this system software engineering, you have to really go through operating system. You have to really go through this compiler design and also this computer architecture, because computer architecture is where your hardware is, right? See, all are logically related. Computer architecture is just like what I shown you here, right? 64-bit, we had this advancement of these registers I could use instead of the cdecl convention in 32-bit. I had to store those parameters, those arguments in my stack. So similarly, see, your hardware will have capabilities. Like I told, that single instruction, multiple data. So based on that capability, you will have your software will improve, right? Because your hardware is holding that. See, because before, if you look at your this video generation, it used to be a software. Now we have a videograph array. Now that part is not done by the software. We have a dedicated hardware for it. So as time goes by, right, all these software codes that you're seeing, you'll have a dedicated hardware for it, because that hardware, because that load on your CPU will reduce, because that hardware will be dedicated for that particular job, and that uh, your load on your CPU will reduce. Okay. So see, these I had to tell you because I was excited in the speed. Okay. So I wanted to pass on that excitement to you. So uh, these won't be directly involved in your compiler. In your compiler, you are not, you just have to see what does compiler do. Compiler will compile down your high level language to an assembly, right? So you are not calling that assembly to call your high level language and stuff, right? That is when you move on to next phases. Like your high level language, you are bringing functionality so that you can call assembly, and from assembly also you can call this high level language. See, right now my aim is just to convert my high level language to low level. To not low level, low level language as in my target machine. So my assembly. Okay. So this is what we finally generate. Okay. So same here. Text is the code section. Okay. Now here, let me run this. Okay. So to run this, this this will generate my object file, right? As in previously we had add.out. Now we can't simply do test.out, right? Why? Because this is a object file. Okay. So NASM, what does NASM do? NASM is an assembler, right? Assembler will convert your assembly to your target machine code. So it is not a executable yet. It is just a pure machine code. Now to make it executable, we need a linker. So previously our GCC would invoke internally a linker, but here we need to manually call our linker. Okay. So it is this ND for linker test.o. Okay. And output it as executable test. Okay. So now if I run test, okay, and remember that exit functionality. Mm, So this 27 is where I had this, right? So if I do, so 27 should be printed out. Yeah, 27 is printed out. So this 3C is that 60 value which I told. What is 3C? Okay, let me not write it here. 3C in X, what is it? 3 into 16 power 1 plus C is see after 0 to 9 we have A, B, C, yeah. Okay. So after 9, A is 10, B is 11, C is 12. Okay. 12 into 16 power 0. So which is 12 plus 3 into 16, which is 48. Okay. So if you add this, you'll get 60. So that's what I put in my VS Code, right? Look at my GitHub here. If you look at here, I'll have this 60 here. This 60 is from here, this hexadecimal 3C. And where did I get this from? If you go at mm, Linux x86 syscaltable. First itself, you'll have this. Okay. So here, if you go ahead, if you look at exit. I have already added this. Okay, I added this in this file. So I have added this plus you can remove out. Okay, let me just add it as it is. Okay. So this is the cheat sheet. So if you look at exit oriented, you'll find this table. So this is where I got that 0x3c. So this is to be added in our RX. Then argument is 0. See, this is your 64 bit. See, remember this RDI, RSI. Argument 0 is RDI. See, argument 0 is RDI. Argument 1 is RSI. Argument followed by till R9. Yeah, see, R9. R9. Yeah. Okay. So that's what it is. So this how 64-bit calling conventions, as I told, right, AMD64 calling convention. Okay, that's been applied here. Same thing. So if you look at exit, so exit has 0x and this int error code. So exit one is exit 0 is what? It is a success. Other than 0 is always an error. Okay, so other values are all nuns, and if you look at this int error code, that is our first argument, this RDI. Now you see everything is linked, right? Everything is linked. See, before you might be like, why was it RAX and why was it RDI? Now you got the answer why it is RDI. See, for 64-bit, that calling convention is AMD64 calling convention. So everything is getting linked right now, right? So this is what it is, and so you don't have to go through all of this. And this last section is what I wanted to say. And see, this video was to give you a motivation of this system software engineering, as I told, and why I was motivated with assembly, and that's why I shared with you guys. So I hope that motivation and that excitement I could pass on to you guys. Okay, so now if now let me just conclude by, see here, this syscall is, see, system call you have, right, which will move from our user space to our kernel space. See, we have four rings, right, of let me show this, four rings was, we just this one. See, ring 0 is our kernel, so it will have total control over our hardware. Ring 1 has little privilege, ring 3 has none. So from ring 3, if we want to move to ring 0, we do a syscall. Okay, that is when we move to our user this ring 0. So ring 0, we have to move to talk to the hardware, right? So that's why. So syscall will do that in conversion from a user space to, because these codes are just user space. We don't have access to the entire hardware. So to get that access, we do that syscall. And this syscall is what? This syscall of our exit, because we passed in this RAX and RDI, right? RDI is our argument. RAX 60 is associated with our exit. So this syscall is invoking our exit call in our kernel. Okay. So that is what it is. So if we run this one, We got this one. And if say if I want to say if I did by this with this I this the last I end after this. So let's say extern add RSI. Okay. And if I call here, yeah, call add RSI. Okay. And let me create RSI. And I will say and I will say just that hmm, this time I'll do add RSI. Yeah. And uh, now this one extern. I just have to make this one visible. So add RSI. Okay. And this was called is just a function. Add into RSI. Uh, RSI or RDI. Sorry, it was RDI, right? So RDI, 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 and also have to change RDI, RDI. So let's say to this 27 adding 10 so that when I do that echo, I'll get 37 instead of 27. Okay. Uh, and RDI. Okay. Now I didn't mention here one thing. See, the start in assembly, right? The start is just like your main function. See, main function is your entry point, right? Just like your main function, this start is our entry point in our assembly. And from there on, we can call all those labels and functions. Okay. So start you can think of as our main, our entry point. It's the entry point of our assembly. This underscore start. And this entry point you'll understand only by this linker. Okay. Whereas in your this NASM command will just be a pure that machine code. It will not know that entry point. That entry point is created by your linker. So linker will create that entry point, the start, where exactly that entry point lies. We have to start from here, this start. Okay. And also that linker will combine multiple objects. So right now, previously we had only one object, right? One object file, just test dot out. Now we'll have to just so if we do this, we'll give test dot out. Okay. Now if we do NASM F64, what was it? Add RBI.asm. Yeah. And if I do add dot okay. And if I do that link, okay, and I have to mention here, I have to also link add dot out. Okay. Then so both of these, if I don't do this, my test will not know this add RDI. Okay. So it's saying reference to add RDI undefined. So I have to put this add dot. Okay. Now it's linked. Now if I run, test is on my final value, right? This test. If I run this, and if I do echo, now I should get 37. I got 37. Similarly, if I do Instead of this one, say 20. So it should give 47, right? So now I have changed only this as a file. So add RDN. Okay. So this add RDN only I have changed, right? So if I do this, okay, that machine code is now updated, and now I have to link it. And now if I do echo, I should have 0. Okay, I got 0 plus I didn't run test. Run test and echo 47. Yes. So this is what you need to understand. And final takeaway is this motivation of this assembly. Okay. So hope you guys liked this and hope you are also motivated and excited about assembly as much I am excited. Okay, then thank you guys. Thank you. We'll end and next one will be of make file, make script. So uh, so we are doing all these commands one by one, right? So make file with just one command will combine all of this. So I explain that in the make file and make script, right? There I'll explain in detail. Fine. Bye.